Pythagorean relationship, a ladder is falling, the 13-foot ladder is propped against a vertical wall, and the ladder falls down the wall. So if we can draw the ladder on the wall, our ladder, I'll call it L for ladder, is 13 feet. Notice this is not changing. This is a constant. The ladder doesn't change. It's falling down the wall because the base of the ladder, we'll call this the base here, is being pushed away or pulled away at 2 feet per second. So they've given us that this is dB dt. Notice, because the base is increasing, dB dt is positive because this base is getting bigger as the ladder falls. If this is the height to this point here, notice as time goes on, the height is decreasing. So dH dt should be negative. I'm not sure what it is. That's the unknown. How fast is the ladder falling? So they're asking for dH dt when the base is exactly 12. Well, 12, I know that we have this Pythagorean relationship here. Base squared plus height squared equals 13 squared, or L squared. But because, well, of course I could put L for ladder, but base squared plus h squared equals 13 squared because the ladder is fixed, and they want to know what happens when the base is 12. So 12 squared plus h squared equals 13 squared. So h squared equals 13 squared minus 12 squared. And so h squared, well, that's 169 minus 144 is 25. So h is 5. Or you could have just known that's a Pythagorean triple. 5, 12, 13. So at the moment when the base is 12, the h is 5. So again, we've got this Pythagorean relationship if it's a right triangle. H squared plus b squared equals L squared. But again, they've told us that the ladder is 13 feet. That's not changing. So this will be my key relationship that I want to take the derivative of with respect to time. Notice that's side squared plus side squared equals hypotenuse squared. The hypotenuse is directly opposite the right angle. So if I take the derivative of both sides with respect to time, power rule and chain rule, 2h to the first dh dt, which is the variable we don't know and we're expecting to be negative, plus 2b to the first db dt is equal to the derivative of a constant is 0. So I could have left this as L, 2L to the first dl dt, but of course if L is a constant, dl dt is 0. So I could have just done that as well. So I want to substitute for h. 2 times 5, the instant that our b is 12, h is 5, dh dt plus 2, they told us when the base is 12, dB dt. Well, look, we have positive 2 feet per second because our base is increasing, so times 2 equals 0. So I'll move this to the other side. 2 times 2 is 4 times 12 is 48. So I get 10 dH dt is equal to negative 48 when I move this to this side. And so dH dt, as expected, I get negative 48 divided by 10, which is negative 4.8, and this is feet per second. Notice our negative rate of change for h simply means that this variable h is decreasing as the ladder falls. So key to this problem is to recognize the ladder is not changing, so dl dt is 0. So ultimately the derivative over here goes to 0. And that if we have a relationship between this side squared plus this side squared equals that side squared, we can figure out how tall this is when this is given as 12. Joe is driving west at 60 kilometers per hour, and Dave is driving south at 70 kilometers per hour. Both cars approach an intersection of the two roads. So here's Joe, good old Joe. He's driving west, and Dave is driving south. And if they keep on going on this path, they're going to hit each other at an intersection. So Joe is going 60 kilometers per hour, and Dave is going 70 kilometers per hour. At what rate is the distance between the two cars decreasing? Well, the distance between two cars, the shortest distance between 2 points is a straight line. So there's the distance between the two cars. I'm going to use a small d for distance. When Joe's car is 0.4 kilometers, excuse me, and Dave's car is, Joe's car is 0.4 and Dave's car is let's change that to 0.3 kilometers. So Dave's car is 0.3 kilometers. All right. So how is this changing? Now, if Joe is going this way, then this distance, which I'll call A, is decreasing. So if the distance is decreasing, then we can say dA dt is negative 60 kilometers per hour. Notice I'm putting a negative there because the distance is decreasing. When it's decreasing, the rate is negative. And this distance, which I'll call B, is changing at 70 kilometers per hour, but it's getting smaller. So dB dt is negative 70 kilometers per hour. Our task is to find this distance here. How is it changing? At the point where B is 0.3 and A is 0.4. So I do know that A squared plus B squared, I usually would call this C, but I called it D squared. So 0.3 squared plus 0.4 squared is going to equal D squared. So when I solve that, of course, I'm going to get 0.5 because it's a 3, 4, 5 right triangle in that pattern. But 3 divided by 10, 4 divided by 10. So 5 divided by 10 is 0.5. So I had to figure that out because if I'm going to use this relationship, A squared plus B squared equals D squared, and I'm going to find the derivative with respect to time, I'm going to get 2a to the first dA dt plus 2b to the first dB dt is equal to 2d to the first dt. Sorry, just had a brain cramp there for a second. All right, so now I can start to plug in for my different knowns. I know that this distance A is 0.4, so 2 times 0.4 kilometers, and dA dt is changing at negative 60 kilometers per hour, plus 2, and B was 0.3, that's the distance, and dB dt was negative 70 kilometers per hour, is equal to 2, and at this moment, D, we figured out was 0.5 miles, 0.5 times dd dt. So when I turn this all around, I can say dd dt is equal to 2 times 0.4 times negative 60 plus 2 times 0.3 times negative 70, all divided by 2 times 0.5. I just did some basic math to give us dd dt is equal to negative 48.79 kilometers per hour. Notice, because I made these two rates negative, because the distance was decreasing, I'm expecting a negative rate for dd dt, and I got it. Also notice that if you do this in your calculator, put a parentheses around the numerator divided by parentheses around the denominator, and let your calculator do all the work for you. Just a reminder of some of the formulas we used for related rates. Circle, area, pi r squared. Sphere, volume, equals 4/3 pi r cubed. Cylinder, volume, pi r squared h. Cube, volume, equals s side cubed. Square, area, equals s squared, where s is the side. Rectangle, area equals length times width, or base times height, whatever you want to do. Remember, with this, you're going to have to use the product rule. Derivative of the first times the second, plus the first times the derivative of the second. Pythagorean relationship, side squared plus side squared equals hypotenuse squared. And you're going to take the derivative using implicit differentiation with respect to time on both sides of these equations.